All right, so here it is, our first YouTube lecture. This is the wave nature of light, or physical optics. We've already covered the ray model, or geometric optics. Now we're going to talk about light as a wave. It's a really good transition from our last unit. Our last unit we covered physical waves, like water waves, and sound waves, which are a special form of physical wave. But now we're going to talk about electromagnetic waves, or the wave nature of light. The, the last one we covered was the ray model, and that's our discussion of lenses and mirrors and refraction and reflection. All of that we did with ray modeling. Now, none of this is to say that light is a ray or that light is a wave. These are different models, and we've talked about before in our modeling that you can learn things from a model and it describes certain behaviors, but it doesn't say what it is. So we're not saying light is a ray, we're not saying light is a wave, but it behaves as a ray in certain situations. It behaves as a wave in other situations, and it can explain that for us. Okay, so what happened was around the turn of the century, this guy named Young, he put two slits in a piece of paper, and up to that time, Newton had proposed a corpuscular theory of light. And what Young said was, well, if light is made of small particles, and these particles are passing through two small slits, I should get two lines. Well, what happened was he got a whole bunch of lines with dark bands between them. And what this acted like was diffraction, just like a wave. Just like if I shout down the hall and the door's open, you can hear me beside the door because the waves spread out once they hit the small opening of the doorway. So just like physical waves, these electromagnetic waves caused interference. It doesn't explain all the behavior of light, but it certainly was a new way to describe the behavior of light that had not been seen before. Okay, so more about the wave nature of light. What we see with our eyes is just a tiny portion of the visible spectrum. You can see it here in the middle of this slide. It's just the middle bit. All the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, is in about 400 to 1,000, about 400 to 1,000 nanometers of light, or 10 to the minus 9. 10 to the minus 9 is the range of visible light. And you can see it goes all the way up to gamma rays, which is 10 to the minus 12, or about 1,000th the wavelength of visible light. Radio waves go from the centimeter range all the way to huge 6-meter range, about 18 feet long. And about a 9 or 10-foot antenna is needed to use these extremely long radio waves. And these very long radio waves can actually bounce off the moon, and ham operators like to use them. Some of the shorter radio waves are about 6 feet, or about 2-meter band, and that's the short end of the ham radio frequency. And those wavelengths at about 2 meters, about 6 feet tall, they can actually go line of sight about anywhere. And they get some funny bounces. They use 2-meter band to talk to the International Space Station and other cool things like that. But even shorter wavelengths, higher energy, shorter wavelengths, direct line of sight, they're not attenuated by the atmosphere. Or excuse me, they are attenuated by the atmosphere. So what happens is they create a zone around them. And that's why we use them for commercial broadcasting. All of our radios, television, satellite radio have very specific set of wavelengths. Now, usually we don't measure it by the wavelength, but we measure it by the frequency. All of these move at the speed of light, which we'll talk more about in a minute. But if you'll remember, the velocity is the frequency times the wavelength. Well, if they all move at the speed of light, or c, then c equals frequency times wavelength. So the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. Every time, always. This happens 100% of the time because they all move with the same speed. Now, generally, 3.0 times 10 to the 8th is the speed of light in a vacuum. And we've talked about how that changes in different media. Like air, it's just slightly slower than that. In a diamond, it's about half that. So, but we'll go with 3.0 times 10 to the 8th because we're talking mostly about air and vacuum. Okay, so you can see that we get more and more energetic as we go to shorter and shorter wavelength and higher frequency. Ultraviolet waves will actually burn your skin. X-rays will penetrate your skin but be reflected by bone. Gamma rays will go completely through your body. Okay, so as you can see, we get to the right-hand side of this picture, we get very, very short wavelengths, very high frequency. At the left side of the picture, we get longer wavelength, lower frequency. Now, interesting, just as an aside, down at the bottom is a temperature scale. And the temperature scale shows the temperature of stellar objects, of space objects that emit at that frequency. So the higher the frequency, the shorter the wavelength, the higher the temperature. And we'll go over some of that tomorrow when we start talking about solving homework problems. Okay? And what we see is just what our eyes detect. It's a tiny part of the entire electromagnetic spectrum, from radio through infrared. Infra just means below. Okay, so infrared, below red, through the visible spectrum, and you can see that little slice is all that we see, from red, orange, yellow, green, blue, indigo, violet. Now, International Physics Union has said something that, we're not going to call it violet anymore, or indigo. They've said they've eliminated indigo from Roy G. Biv, but that just makes it hard to pronounce, and so we're going to go with Roy G. Biv. So here you can see, but violet, above violet, is ultraviolet. Okay, so that's what our eyes can't detect. So this big white bar across the picture here shows the entire electromagnetic spectrum, but we can just see what's in the middle. Birds tend to see in the infrared. That's why birds tend to pollinate flowers that are red. Bees and other insects tend to see in the ultraviolet range, above where our eyes see, and that's why they tend to pollinate blue flowers. Now, this doesn't always hold true, but it's a pretty good estimate. Dogs and wolves see in the infrared. Well, infrared is heat. That's really useful for them. Okay? If you're a predator, you can see not only will your prey stand out against a cold background, but you can see where your prey has been. Your dog can see your footprints as you walk across the room. Your dog can see which chair is warm that you've been sitting in. It glows to them. So they can actually see, and we can tell this by the shape of the rods and cones in the eye of the animal we're looking at. That's how we can tell what frequencies and wavelengths they can see, which is always really neat. Okay, so speed of light. Before 1700, they thought light instantly went from one place to another. And, I mean, when you turn on a light switch, you see the light right away. And so well, of course, it just travels instantly. Galileo worked on the speed of light, and he got a really close number. He was within about 10%, but he just couldn't believe it was that fast. Ole Romer was a European scientist, Swedish, I believe, and he said, you know, I really think light has a speed that it actually reaches us somewhere. A. Michelson measured the speed of light between two mountaintops in California, and that experiment is known as the Michelson-Morley experiment. And the physicist who worked with him is a distant relative of mine. But Michelson-Morley, they went to California and measured the speed of light between two mountaintops. They had a spinning mirror, and they were able to determine by spinning the mirror how fast the light was traveling, because the time it took for one mirror facet to move from the projected light to the reflected light, well, that was how long the light had taken to travel between the two mountaintops. And they used California near Los Angeles because the hills were about the same height and the air was particularly clear. A little ironic these days, but they used California just because there was less air pollution, and so they could conduct the experiment in clear air. That experiment would be almost impossible almost anywhere today because of the levels of air pollution. But luckily, with the invention of lasers, we've been able to find it much, much better. Lasers emit a single monochromatic light. Every wavelength that comes out of the laser is the same, okay, within very, very small tolerances. And that allows us to find the speed of light very carefully through diffraction. Okay? So we've been able to determine c, or the speed of light, to very, very small tolerances. And remember that for all of these electromagnetic spectra, that the velocity is c. C is the speed of light, that's the velocity, and it's the wavelength times the frequency. So 3 times 10 to the 8th is going to be close enough for anything on your AP exam. Just 3.0 second EE 8. That's your speed of light. Good enough. That's going to be close enough. The other thing about wavelength that I want to put in here is if you have a 400 nanometer wavelength, well, that's going to be 4 times 10 to the 7th meters. Don't bother with that. Most of the wavelengths you're given for light are going to be in nanometers, which is 10 to the minus 9th. Just remember that one. Your calculator will interpret it for you. So if you have a 738 nanometer wavelength, in your calculator put 738 second EE, the negative key, which is the little minus sign in parentheses at the bottom, 9. So that will put in 738 times 10 to the minus 9th meters. Okay? Don't ever bother converting. Just for a 450 nanometer wavelength light, put in 450 second EE, and then the little minus sign at the very bottom in parentheses, 9. And it will convert it for you. Your calculator is smart enough to understand that. You pay $100 for it. You look like a nerd carrying it around. Use it. Okay? This is one of those areas where you're going to sacrifice speed for prettiness. Don't be pretty. Your calculator will take ugly or bad scientific notation and eat it up. Use that ability.